So we've been working on gravity and the force of gravity and calculating the force of gravity and then applying that force to circular motion to calculate things about orbits. I want to show you something else that comes out of it as well. We had the force of gravity was equal to gmm over r squared. But you guys have been calculating the force of gravity for some time because, of course, that's just the calculation of weight. But what you guys have done in previous stuff, especially in grade 11 and stuff like that, is you could calculate the force of gravity or weight as just mg, which still applies. There's no difference. You could calculate your weight on Earth by using mg or your weight on Earth by using the gmm over r squared. But with that idea, if we cancel off your masses, we are then left with an expression for just g, where gm over r squared can be used to calculate the acceleration due to gravity for any mass at any distance. Because obviously, the further away you go from the Earth, gravitational acceleration will get lower. And this is how you can calculate it, just by putting the two expressions together and canceling off the mass of the second object. You end up with the gm over r squared, which can be used to calculate the gravitational acceleration at any distance from any mass that you want. So it's a different way to calculate g. So take something really simple, for example, finding the g value of maybe the sun. So we'll bring in the sun. So here's the sun, and you want to know the gravitational acceleration on the surface of the sun. Well, all you need to do is take the 6.67 negative 11, you multiply that by the mass of the sun, and then you divide that by the radius of the sun squared, and you will have the gravitational acceleration on the surface of the sun, which obviously should definitely be more than 9.81. So if we put in all of our values that we have, g, mass of the sun, radius of the sun, you should get an acceleration of about 274 meters per second squared, which is quite a bit. So if you compare that to Earth, it's about, like 27, 28 times the acceleration due to gravity on Earth. So it's a considerable acceleration. So even just falling for like 3 or 4 seconds, you'd be like going like 1,000 meters per second. So that's just a crazy acceleration because the high mass of the sun. Big radius, but mass is gigantic. So this is how we can calculate the gravitational acceleration of different things. Even take something else. Take like the good old-fashioned. Take the moon. Okay, most people know or have an idea that on the moon, gravitational acceleration is about 6 times less than it is on the Earth. So if we would take about 1/6 of it, the moon has got an acceleration of about 1.6 meters per second squared. Well, if you know the mass of the moon, which is on your sheet that you guys have, and it's about 7.35 times 10 to the 22 kilograms, you could find the radius of the moon using this type of information. So the radius of the moon would just be gm over g, and then don't forget to square root it. So you got the 6.67, you've got the mass of the moon, divide that by not 9.81, but the 1.6, and then square root it, and you should have the radius of the moon. And this should give you approximately 1.75 times 10 to the 6 meters, which is in fact approximately the radius of the moon. So this is something a little bit different using just part of the expression we're using before. You can calculate the gravitational acceleration for any mass at any distance, anything you want. Even if you go back to, say, the Earth, you can look back at the Earth, and you have the satellites and the space station, which are orbiting the Earth, relatively close. You can actually see just, the radius difference isn't that great. And people think about, there being almost no gravity at the space station and the satellites and that type of stuff, or the space shuttle when it's up there. But really, the radius, since the radius is measured from the core of the Earth, the radius hasn't really changed that much. And therefore, the acceleration due to gravity hasn't really changed that much. In fact, the gravity up there is maybe 10% less than it is here. So it's not that they don't have a lot of gravity up there, but since they're in orbit, they're in constant free fall, so it seems like they're floating, but they're actually just falling. So a really simple expression to calculate the acceleration due to gravity. Okay. Next we're going to do, though, is we're going to show you what this can be applied to in terms of something else. So let's get rid of all this stuff, and we will show you what else this leads to. So let's show you what you can do with that whole gravitational acceleration thing. Now that actually connects to another one of the measurements you guys have done a lot of work with. Now, first things first, I'm going to just draw like the surface of the Earth here, blah, blah, blah. Now we get some water in there, so we've got some water. All right, good enough. Okay, so suppose you are floating around. Let's say you're here. There's, oops, wrong color. There we go. Okay, so there's you, and you're, I don't know, you can magically float above the Earth. Now, this is connected to what you guys have been working on before. Of course, you are going to fall down to the Earth. Now, the reason, of course, you are going to fall to the Earth is because you have potential energy. And of course, since you have potential energy, you are going to fall down because the Earth's gravity, of course, pulls you down. Now, if we're going to calculate your potential energy, well, what you guys done before here, you calculate mgh to calculate gravitational potential energy. But this doesn't quite work the same way anymore because your g value is not necessarily going to be 9.81 anymore. So what we need to do is we need to look at this a little bit differently and incorporate that changing g value in order to figure things out. Okay, so what we're going to do is we're going to change the situation a little bit. We're going to take the Earth, and we're going to get rid of this right here. So let's get rid of that Earth right there. Oops. And we will do, there we go, that's better. Okay, get rid of that, and then we can get rid of this right here. All right. Now, suppose we instead have you really, really, really far away from the Earth. So now the Earth is over here. So there you are, way, really, really far away from the Earth. Now you have potential energy. The Earth can pull you, and you have potential energy. No problem there. But let's adjust how this works. If you've got potential energy is equal to mgh, that's fine. No big deal. But your g value isn't just 9.81. Don't tell me that when you're way up here, gravitation's going to be 9.81. You're way too far away. On the surface is 9.81, but not way up there. So we need to incorporate that into here. So the g expression you just worked with was gm over r squared. So instead of using this, what we need to do is put this expression into here. And that's going to give us m and gm over r squared times h. Now we're going to specialize this a little bit as well. Okay, you're going to take care of something. If we look at your classic potential energy type thing you guys have worked with, the h should be measured from where you are to the surface of the planet. That would be your height. But in terms of gravity, when we do the radius, that is from your center of gravity to the Earth's center of gravity. And there's the r value. When you're talking about stuff in space and things are so far away and all that kind of stuff, those two values are almost identical to each other. The difference between them, that tiny little difference between them, as you go really, really far up, that difference becomes so insignificant that these two values can pretty much be considered to be equal to each other. So if that's true, we can go back to our expression over here. If this h up here is pretty much the same thing as the two r's down there, it actually helps to cancel off one of the r's. Okay, and it cancels off the h up here. So the h on the top cancels off one of the r's at the bottom. And what we're left with then, we'll rearrange this a little bit, is gmm over r. And this is how we can calculate the potential energy of a mass at any distance from any kind of mass we want, and it incorporates the whole changing g value into it. Now this is called This is often called the general form of MGH, or sorry, a general form of potential energy, which can be used in any situation. And this what's typically used to find the potential energy of objects that are on gravitational fields that we don't know, or they're falling through space and stuff like that. It just works a lot better. Now, one thing you've got to be careful with, though, is how it actually works. If we go back to what you guys used to do, if we took this guy and we moved him farther away from the planet, say he's going higher, if we went to, let's call it classic MGH, classic potential energy, you'd say his height's bigger, which means he's got more potential energy. But that's kind of not the way it works. Because if we go back to the newer thing we're working with, if we use the GMM over R, as the radius gets larger and larger and larger, as this value down here becomes larger, the potential energy actually becomes smaller. So as you go farther away, your potential energy actually goes down. So that's one of the differences. So if you increase the radius, you actually have less potential energy. Now this actually makes sense, because if you go farther and farther and farther and farther away from a planet or the sun or whatever you want, there's less potential for it to pull you back. The closer you are, the easier it is for it to do something to you. So the farther away you go, there's less potential for something to happen. There's less potential for it to pull you back. You have less potential energy. Okay, so that's an important distinction between the two. As you increase your radius, there's less potential energy. There's actually less potential for it to pull you back. Okay, and that's a really important mindset to have in something like this. So it's a different way to look at it, but it actually makes way more sense than the classic MGH. The farther away you go, the less potential there is for it to do something, and less potential energy you're going to have. Okay, so then what happens if we take this guy here, and we're just going to move him over here a little bit. We're just going to move him over here, and let's just take the situation here where we know he's up here above the Earth. Of course, he has potential energy up here. We know that. So here he's got potential energy, and what he does is he begins to fall to the Earth. Well, as he falls towards the Earth, his potential energy actually goes up, because he's getting closer and closer and closer. And at the same time, which seems kind of weird, is the kinetic energy also goes up, which is different than what you guys had before when you did classical mechanics, whereas one got bigger, the other one got smaller. And this is where a really, 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 really important mindset kicks in for this as well. It's not about how much energy you have, it's about how much your energy changes. And it's really important to look at the change in potential energy will be equal to the change in kinetic energy. And that change is really, really important. It's not about how much you have, it's about how much the energy can change. Okay, so the change in potential and the change in kinetic will be the same. It's not about how much you have. Okay, so you need to be able to change your energy in order for it to do something. So for example, when you're standing on the Earth, when you're standing on the ground, you have huge, massive amounts of potential energy, but it's not good for anything because you can't change it. And that's why you don't get any kinetic energy, because you can't fall down. So unless your energy can change, it's not really good for anything. And this is actually going to be really important for electric fields as well. So again, it's not about how much potential energy you have, it's about how much the potential energy changes. And the change in potential will always give you a change in kinetic for what you guys do, and that's how you can solve for things like how fast they would be going when they fall. And that's what we'll get into next.